Hello everyone, welcome to my YouTube channel Learn to Code. In this video, we are going to talk about problem 1319, number of operations to make network connected from lead code. So, as you have read the question, basically in this question, we are given few disconnected components of a graph. Our task is to connect all of them in the minimum number of steps. So what are these steps? In one step, basically, we can take any edge and connect any of the two vertices from that edge. That means in this example, this edge is removed from here and then 1 and 3 are added from that edge. It is not necessary that the edge should be either be added to 1 as a vertex or 2 as a vertex. If there must be some other component, name it 4, then we could also add this edge to 3 and 4. So as we know that for a graph to be connected, if there are n vertices, we need at least n minus 1 edges. So our first task will be calculate the number of edges. And if the number of edges are less than n minus 1, then we can return minus 1 as stated in the answer, because it is not possible to make the graph connected. Now, how are we going to do this? To do this, a connected component of size k requires only k minus 1 edges to make it connected. If there are lesser than k minus 1 edges, then it is not connected, and if there are more, we are free to remove one of those edges and use it wherever we want. So, and how are we going to do this? That means that in this question, as firstly, we need to take into consideration the number of different connected components, and then one by one we are going to add. So supposingly, if there are 5 number of connected components, that means we need at least 4 edges to do so, and that will be our answer. So basically the question boils up to the point that now we need to calculate the number of different connected components in the given graph. So one way to do this is make a graph from these edges and then traverse using DFS and count the number of connected components. But the simpler way will be using union find algorithm. So if you are not familiar with union find algorithm, I'll request you to read about it and then come again to the question. So let's start with the union find algorithm. So as we know, in the union find algorithm, firstly, we treat each and every vertex as a single component, and edge by edge, we make them connected. So let's start by a vector root. So this vector will basically denote that which connected component is our current vertex a part of. This means that root of a vertex will basically give us an identity that this belongs to this component. This vertex belongs to this component. If we see in the example, then supposingly if we take 0 as a base root for this connected component, then root of 0, root of 1 and root of 2, these all will be equal to 0. So let's initialize this root. So basically right now we have initialized our root vector where each and every vertex is its own single component. So after this, what we are going to do is connect each of these vertices one by seeing the edges given in the connections vector. So let's traverse the connection vector So now we got our two vertices which are connected through this edge. So our task is to make these two vertices belong to a same connected component. So basically what we are going to do, we are going to find the roots of these two vertices. So let's term them as R1, which is equals to root of vertex V1, and find R2, which is root of vertex V2, and write the following function find. Now in this function, if root of some vertex is not equal to that vertex, this means we need to traverse this vertex one more time towards its parent. Or else, as if root of vertex is equals to vertex, we are going to simply return this vertex. So basically after finding these two roots, now if these two roots are equal, then this means they are already connected. But if they are not, component. So to unite them, simply what we can do is root of R1 is equals to R2. And these two vertices now belong to a same connected component. You can also do it either way. Root of R2 is equals to R1. But for right now, I'm going to do it like this. Now as we have traversed to each and every edge, and we have initialized all the roots from the specific indexes or vertices, we can term that root of a vertex will give us the connected component which it belongs to. By that I mean that root of 0 will give you 0, root of 2 will give you 0, and root of 3 will give you 3. So now our task is to count the number of connected components in this graph. And how are we going to do so? Simply by observing our terms, we can say that here root of 3 is equals to 3, and in this connected component there is only one vertex which root's value is also equals to the number of that vertex, that is 0. Root of 0 is going to be 0, but 1 and 2 are having the value 0 as their root. So this means if root of a vertex is equals to vertex, it represents one single component. So count the different number of connected components, we can simply do a for loop in which we traverse to each and every vertex, and if the root of that index is equals to itself, this means it denotes one connected component. And as we earlier discussed that if there are two connected components in our graph, then we only need one such step to make it connected. So our answer is going to be answer minus 1, and we are going to return that in our function. Again, there is one more way by which you can find the number of connected components, and that is simply count the number of unique root values. That means that if the number of connected components are 4, then you can traverse to our root vector and count the number of unique elements. It is definitely going to be 4, because either a vertex is going to represent itself as a root, or its parent vertex is going to represent itself as a root. So either way the answer will be same, and the answer to this problem will be answer minus 1, number of connected components minus 1. So thank you for watching the video. I hope you got the basic approach by which we solve the question. If you have any doubts, please let me know in the comment section, and if